Thanks a lot, Suranga, actually, also being invited and having, kind of all of these impressive co-speakers and so on, especially going after Mark is, I think, super hard, but I'll try to give something entertaining. And yeah, and also congratulations to you for the 10 years, and kind of your work also is quite yeah um yeah, inspiring for us and for the whole community. So, okay, I'll share my slides, I think.
Yeah.
Wait. Okay. So for this, I'm actually trying something new today, which might fail. And if I'm disconnecting, please bear with me because I'm not so sure if everything works. So maybe before I share my slide, maybe that's easier to see like this. So right now, what I'm doing is I'm sharing my EDA and my heart rate. So I'm wearing the an EDA sensor. And so green is EDA. So if you're saying something interesting also for the later talks or so on, then kind of you should see spikes in the EDA sensor on the heart, and the red ball on top of me is the heart rate, is my heart rate. So maybe kind of it goes up, so you see fluctuating or so on while I give the talk, and when later on I might relax. And the blue and the pink lines are the my EOG. So this is from the glasses. So now if I blink, is a bit hard to see because my uh, thing is in the way, my microphone is in the way, but you see blink, and I think left and right will be easy. So if I'm moving left, right, left, right, left, right, you should see the change in the signal. So this is vertical and horizontal from the nose bridge. So anyways, and as I said, the setup here right now is a little bit I played around with it last night for we also East Week and Ubicom is going on. So I played around with it and it might crash, but let's see. Let's see if I get over the talk with that. But anyways, so my talk today is, I mean, I'm really in the lab spirit as well. Kind of I really want to augment human senses, and I also want to look into, and that's why I'm also trying this demo right now, into can we use more creative ways to use sensing and actuation. So on that level, kind of you have a lot of those, I would say, tracking applications, fitness tracking or detecting other things from sensor signals, also in Ubicom and eSwig. And I find that always a little bit boring and a little bit, I would say, yeah, too easy, kind of to also work towards a surveillance state. And I would just also wonder, kind of, can we use sensing? Can we use technology to, really on one hand help people? And I think there, Suranga, your lab is awesome, and I really like the assistive technologies that came from you. But also, in another sense, also to build stuff that is also fun and that is actually then in a second step maybe also helping us. And that's the outline also for my talk. So I'll talk a little bit about my personal background. I'll go into a little bit of physical activity recognition. So this is kind of where I came from, and this is also where the criticism that I'm raising here maybe is also strongest. So kind of not just detecting things, not just detecting affect or activities, but really trying to do something with it. So really, can we use it to augment ourselves? And then at the end, I'll go over the collective augmentation, last part of the thing. So my background is in Ubicom and eSwig and wearable computing. And early on, I recognized that kind of if we're dealing with this type of technology, if we have a lot of computing around us, the limiting factor is no longer CPU speed, RAM, or other things, but the limiting factor is really the human attention. So you see two of my desks, one at PARC, one at Passau. And I early on recognized that, yeah, there's a problem there. There's a human attention problem if you have 40, 50, 60 sensing devices around us. And that's why a lot of my early work really focused on activity recognition and context-aware systems. So having sensors with you that understand what you're doing, and then kind of try to help you in applications. And that was then also the early work that was also doing the PhD. So maintenance work, or work in industry. So with Skoda, with Zeiss, we had also application scenarios with the Paris firefighters. And however, seeing that these devices also became mainstream, I got more and more interested in what's going on in your mind, kind of more on the cognitive side. So I first started also to look into kind of cognitive activity recognition, or kind of getting small pieces about what is happening in our mind while we're interacting with people. And there was kind of this problem when I looked into neuroscience, that kind of you see these type of setups. So kind of and I don't want to ridicule the researchers here, because this is really impressive. This is magnetic based brain sensing, I think Nottingham and UCL, and that's kind of the state of the art where we are right now. So you don't have to lie in a big magnetic resonance. It's not really how we interact with the world, and we see that now more and more, that kind of also cognitive scientists. I hope my internet is doing okay. At least the streaming works okay. I'm sorry if there's an outage, because I have to reroute a couple of things so the live demo is working. And so then I try to figure out, can we understand what is going on in our mind, what is going on cognitively in using everyday sensing. Kind of, we started out with eye tracking. We worked over, devices with Google Glass, tablets, and then since 5 years, I'm actually working with Jeans, so a Japanese glasses company, on Jeans meme. So you see, I'm wearing one right now. It's still not completely unobtrusive, but it's kind of getting there. It's getting better. In this case, this is EOG, so it has 3 electrodes around the nose. I can show, if I'm not destroying anything, one here again. So you have the 3 electrodes. With this, you measure capacitance, and you can get the relative eye movement. So blink, and as you see, kind of strong left and right movements are easy to.
I think we are experiencing Kai's experimentation effects. Hopefully he'll be back in a moment.
Algorithms can tell you how tired, how alert you feel throughout the day using the eye movement. So in this case, kind of usually if you're getting more tired, you blink more. Actually, also if you're nervous, so like me right now presenting here, you should see, kind of higher eye blinks. Also, if you're talking to other people, you have actually slightly higher eye blink rate. If you're getting tired, you keep the eyes closed a little bit longer. And these type of things you can recognize over the glasses, and that's something that we modeled. And then, kind of in a second step, we also tried to then improve habits over this. And I'm kind of happy that this finally got accepted. So this is actually co-work with Woo-Tak Woo, and also with Mark and Yusun Pai, who was actually also just, I think, downstairs or upstairs from you just a couple of months back. And he joined us now back in Tokyo. And what Pai did was using the sensors from the Jeans beam. So actually he took a Jeans beam apart and put it into a VR headset to try to augment sleeping. So in that case, he tried to get people to nap in different VR environments. And one interesting side note, so we can also do sleep onset detection or other things, but one interesting thing, I think it was not statistically significant, but what we saw is that there's a slight quicker onset in sleep if you're sleeping in your own bedroom in VR. And I found that was quite interesting from the study. So people had the different environments, some things that they could choose to fall asleep or to nap. One was a 360-degree video of their own bedroom, and it seemed that had a slight effect on people. So I found that kind of an interesting thing where people could dig a little bit deeper later on as well. So then moving on, so we did these cognitive studies. We tried to optimize some interactions using these relatively noisy but unobtrusive sensors, and we kind of did also the same for interactions. And I think there is also still the the place where I'm not really sure what will work and what will not work, and where we played with a lot of different ways to then do subtle interactions with devices. So one thing is Cho Young's work with nose interaction, so swipe left and right, that we then also took apart, and we can now also detect face touches or similar if you're closer to the nose. You can also see in my signal behind, so if I'm doing a left swipe on my nose versus a right swipe on my nose, because you're moving the electrodes on the skin underneath the electrodes, it's quite visible. So yeah, that's one thing we looked into. And then moving on from the cognitive, I then got more and more interested in, or I get more and more interested in, really augmenting ourselves. And this is still ongoing, and I'm learning a lot from other keynote speakers that were here. So Jürgen Steimler beforehand, and also, of course, Inami Sensei, and also Mark's work in these cases, where we are really trying to build systems that can augment our body schema. So this is now a small work with Kota here at KMD, where one of our master students actually added a camera on top. This moves mechanically. And what I really liked about this, it gave you a 360-degree neck. So you can move your neck, not just the limited amount and just have the 120 degrees vision, but you can really have a 360-degree move around, and you can also look on the ground behind you. And what I found fascinating about this was really that it seems very seamless. If you wear this, you get used to the lag, so there's a little mechanical lag. But after a while, you just feel, oh, this is how kind of my vision was beforehand. And I find this intersection of really then augmenting and integrating our systems closely to our own body fascinating. Other works is also, so this is together with another co-speaker here, Pedro Lopez, where we used artificial muscle to learn you drumming. So kind of the arms move themselves. And here again, a little highlight that is also not really in the paper was when I used this, and then when we kind of change the air pressure, what is interesting is there's an intermediate step where sometimes I really feel that the system drums. So it uses my arms and it drums. And sometimes in between I'm drumming, and then there's this in between where I'm not really sure if I'm drumming or the system drums and uses the system. So it's one thing. And then later, also, this is something we just presented yesterday at EastWeek and UBICOM, to use also peripheral vision occlusion. So that's something that we have often in VR and in VR settings, that we kind of reduce the peripheral vision so we don't increase motion sickness. And we took the same principle and we just put it into a wearable form factor with opaque switchable film. So then you can actually reduce motion sickness in people that go on a train ride or so on. Now moving over, so these are kind of the dabbling from my side from just the sensing part into the augmentation part. And what I'm actually really interested in is the collective augmented or the collective augmentation part. It's something Mark mentioned before with the hyperscanning and also the synchronization. And I really wonder, kind of, can we use that also for interaction? And I got inspired by work from Jamie Ward and also Kelly Hunter. So Jamie used the sensing in interpersonal synchrony in an inclusive theater workshop setting for autistic children and people on the autistic spectrum, and showed some interesting work there. And we continued this and looked into head motion and eye blink also with the Chin's meme sensors. And what we could recognize is we could kind of replicate some studies in psychology that show if we are facing each other face to face and talking to each other, we have a higher head nod and eye blink synchrony than if we're facing back to back. So there's something going on when we're talking to each other, when we are interacting with each other in social interactions, that there's a signal there, and kind of it might get weaker or stronger depending on also what we like and don't like. I think that is quite fascinating. And from that we thought, okay, can we do something where we visualize this, where we show a little bit what is happening in a collective environment? And we wanted to do this in performance, in an art performance part. And first we thought, oh, we want to use eye tracking and so on, but there were a lot of issues with trying to use eye tracking in that setting. So one was first we tried pupil labs, but then kind of we could get 10 pupil labs hooked up, but people really didn't like to wear that too much. And the other problem we also had with pupil labs was people felt excluded in the audience. So if you have just 5 to 10 people in the audience with the sensing, at least the feedback from other audience members where they felt kept out of the loop. So what we tried then was we used these type of sensors, so the EDA and heart rate, and we had really all of the audience member stream the heart rate on stage, and we changed then the lighting, the sound based on the sensing data. And that, of course, then changed again the dance. And I can show a small video. I think I forgot again to add the sound, but I think you can just get a little bit of the impression of the dance performances. So we had 3 dance performances with 60 members where we streamed the sensor data live on stage, and we created this type of feedback loop. We hope we created it. We cannot really say because it's very hard to evaluate feedback loops. I think that's also something that from other types of research. But overall, kind of on an architectural point of view, it was actually a success. So we could get all of the sensors. Other thing that we took out of it was also, you saw a little bit in between raw data streaming, and that was also quite successful. Actually, people like to see the raw data and see, kind of don't, if you're trying to do visualizations, like you see also behind me right now, actually maybe sticking to something that is more raw data is sometimes a quite good idea. And overall, so we had the performances that worked well. However, also interestingly, we could also look into the sensor data afterwards. And just this is something that is still explorative, and it's still under review. However, what you see here is the 3 performances that we did, and you have the PNN50. That's the only thing that I will just talk about now. That's a heart rate variability feature. And what is interesting is at the beginning of all of the 3 performances, PNN50 is relatively low. And that's the aggregate over all 60 audience members for each. So you have this, kind of, there's some kind of synchronization happening, because if you see also the error bar in light blue, it's not so big. And then what happens in around 30, 35 minutes is PNN50 goes up. And that means people feel more relaxed. So there's tension at the beginning of the piece and there's relaxation later. And what's fascinating is this corresponds with the choreographer's vision for the piece. And we see this actually more and more in the data, that you have this link between the choreography and what was laid out by the choreographer and the sensor data. And to wrap things up, we're working on a novel hardware setup. So you saw the old one that we used for the performance and the new one that I'm wearing right now. So we can stream up to, I think we tested 150 or so on people right now simultaneously. We can calculate features on not really real time, but with a 1 minute, 2 minute delay. And we actually continuing this work. So this is kind of new work, just a small poster in the World Haptics where we looked into aesthetic chills in classical music. So if some people, if they listen to classical music, they get frisson, it's called. And we're trying to also use this to first detect it in some people and then also transmit it. So frisson waves. In this case, there's Peltier elements in the back of your neck that then actually activate a cold feeling. That's also related work from Petty. Petty did some experiments on that level as well. And what we now build is we're also streaming all of the sensor data. We have a real-time frisson detection algorithm. And then we try to trigger frisson in the people that's surrounding you and want to see if this creates more frisson in a particular group. So that's about it. There's also, I have a new project that looks into accessibility assessment, and I want to use these devices and put them into different form factors. And at the end, of course, a special thanks to everybody involved. There's, kind of a huge group behind that. And I'm just a person presenting. These are the people that do the actual work. So thanks a lot.